Okay, today we discuss vectors in the three-dimensional space, specifically what is so-called R3. One-dimensional space, just the real line is R1. The plane is R2, and the three-dimensional space is R3. So here we need three axes: X, Y, and Z. X-axis, Y-axis, and Z-axis. In order to imagine that how it looks like. So suppose that the X-axis sticks out of the screen. Y-axis is this, and Z-axis goes up. Of course, it's a little bit complicated to show a three-dimensional thing on the plane. So that's why I said that X coordinate sticks out of the plane or sticks out of the screen. Now, every point in the space has three dimensions, can be shown by three coordinates. So please pay attention that like axis X is perpendicular to axis Y, makes it an angle of 90 degrees or pi over 2. So this angle here is a 90-degree angle. Again, since we are showing this on the plane, it might not be clear, but imagine that X-axis is coming out of the plane and is perpendicular to both X-axis and to Y-axis and Z-axis. The same thing as Z-axis, this is more clear here, is perpendicular to Y-axis. So these three axes are mutually perpendicular. So if I have a point in the space, suppose I have this point. First of all, if I project on the Z-axis, I will get the Z coordinate of that point. For the X and Y coordinates, suppose when I project on the plane of X, Y, we land here. Then I project that on the X and Y axis. Again, all of these are right angles, but since we are drawing these three-dimensional coordinates on two dimension, it's not very clear that they are right angles. So this point, suppose is a point A consisting of three coordinates. What I have here is A1. In this example, in this picture, A1 is positive because it is in the positive direction of X-axis, but if it falls on the other side of the origin, A1 would be negative. So this is A1. This point, this number here is A2. And this number here is A3. The Z coordinate is A3. So every point in the space is determined and uniquely identified by three coordinates: X coordinate, Y coordinate, and the Z coordinate. Similar to the case that we had for R2, if I look at this vector initiating from the origin, and as you know, origin is 0, 0, 0 in this case, so this origin is the point 0, 0, 0. So the vector that starts from 0, 0, 0 and terminates at the point A, this vector. Let me show it by bold U, or let me put an arrow on that to emphasize it's a vector. So vector U, its initial point is the origin, 0, 0, 0, and its terminal point is A1, A2, A3. The way that I show that, very similar to the two-dimensional case. I use this, instead of parentheses, I use this notation. So it's going to be A1, A2, and A3. But for a point A, I use parentheses. A1, A2, A3. But for the vector, we use the notation that you see. So this one is a vector in R3. And this is a point in R3. Similar to the to R2, we have another notation to show a vector. Another notation for the vectors in R3. So this vector A1, A2, A3 can be denoted by A1I. Again, I should make this I bold, or here to show it's a vector, I draw a vector sign on that, plus A2J. And we had these two vectors, I and J, in R2. But here we need one more, and that is vector K. In R2, I was what? The vector starting from or initiating from the origin, ending at 1, 0. But here, this I means starting from 0, 0, 0 and terminating at 1, 0, 0, because everything should be denoted by 3 coordinates. So in this notation, I is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. So if I want to show them in the three-dimensional space, again, this axis that sticks out of the plane is x-axis. This horizontal one is y-axis, and this vertical one is z-axis. So what is I? On the x-axis, find 1. In fact, this 1 on the y-axis is 1, 0, 0. This point 1 is 0.1, 0, 0. One, 0, 0. But the vector that connects the origin to this point, this vector, is vector I. This is vector I. Or just let me write a little I next to that. So this is vector I. In a similar manner, if I find 1 on the y-axis, that 1 on the y-axis in 3 coordinates means it is 0, 1, 0. And the vector initiating from the origin and terminating at that point, this vector is vector j. And finally, on the z-axis, if I plot 1, meaning that that point right there is the point 0, 0, 1. And the vector initiating from the origin and ending at that point is vector k. So this was vector I here, vector j here, and vector k here. All of these vectors are unit vectors. Their length is equal to 1. Now the question is, how do we define the length in 3 dimension? The length of a vector in 3 dimension, similar to 2 dimension, but we just have one more term under the radical. So let me talk about that as well. The length of a vector in R3. So if I have a vector A1, A2, A3, the length, as you might remember in R2, we use the same notation. This means the length. The length is defined as a radical of, in R2, we just have the first coordinate squared and the second coordinate squared under the radical. Here, we have the first coordinate squared, second coordinate squared, and the third coordinate squared. If I want to use the other notation for a vector in R3, so A1 I plus A2 J plus A3 K, the length is going to be the same as I said, radical of A1 squared plus A2 squared plus A3 squared. For example, find the length of this vector 1, -3, and 2. So please pause the video and solve this on your own before looking at the solution. Please pay attention that you need to simplify your answer as much as possible. So here the length of this vector is going to be radical of first coordinate squared plus the second coordinate squared plus the third coordinate squared. 1, -3, and 2 will be put inside these parentheses. 1 squared 1 and -3 squared 9, 2 squared 4. So 1 plus 9, which is 10, plus 4, 14. Radical 14 cannot be simplified more, so that's the final answer. If we're able to go further and simplify the radical, we have to, but radical 14 cannot be simplified more. So as the exact value of the length, this is the length of this vector. Okay. And similar to the case of R2, I mean the plane, the two-dimensional plane, when 2 points are given, we can find a vector initiating at one of the points and terminating at the other. We have the same situation here. So suppose we have 2 points, like P in the plane consists of A1, A2, and A3. And another point in the plane consists of B1, B2, and B3. In an actual example, these A1, A2, A3, and B1, B2, B3 are given numbers. These coordinates could be positive, negative, or zero real numbers. Okay, now suppose I want to find the vector from P to Q. So similar to R2, I subtract the first coordinate of the initial point from the first coordinate of the terminal point. So that's going to be B1 minus A1. The same thing for the other coordinates, B2 minus A2, and the third coordinate, B3 minus A3. Or if I want to show the same thing, PQ, in the other notation, B1 minus A1 is multiplied by I, B2 minus A2, I put inside parentheses, by J, B3 minus A3 So this is the vector connecting P to Q, or we call that the position vector from P to Q. So these are the position. So the position vector from P to Q. So pay attention that the position vector from Q to P will be different, because if Q is the initial point and P is the end point, then like the first coordinate of the vector, instead of B1 minus A1, it will be A1 minus B1. The second coordinate, instead of B2 minus A2, will be A2 minus B2. And the third coordinate, instead of B3 minus A3, will be A3 minus B3. So that PQ and QP are parallel, but they are in opposite directions. Just a simple example. Part 1, find the position vector from the point 2 minus 1, 4 to the point 5, 6, negative 10. So from here to there, meaning that when I find the position vector, as usual, before looking at the solution, please try to do it on your own. Then so you can pause the video and then you can watch the answer to see that if you get the same thing. Okay, from here to here. So the vector sign, depending on how the answer, sometimes it specifies use this notation, or sometimes it is specified that use ijk notation. So something times I plus something times j. Here on the slides, I use arrows on I, J, and K, but in general, they are like bold letters. So you don't, you don't see arrows, it's okay. Still, they mean they are vectors. Plus K. I will show in both notations, but in a problem, in a homework assignments or anything like that, pay attention that which kind of solution, which kind of form you need to show your solution. So in any case, the first coordinate is the first coordinate of the terminal point minus the first coordinate of the initial point. 5 minus 2, which gives me 3 here. Or in the other notation, 3 goes here. 6 minus negative 1, which is 6 plus 1, will be the second coordinate. 7 or 7 here. And minus 10 minus 4, which is negative 14 or negative 14 here. So depending on how the answer was supposed to be written, have 2 ways to show them. Yeah. Now, part 2 of find the length of the vector we just found. Again, pause the video and try to find on your own and simplify the radical if it can be simplified. Okay, so the length is going to be equal to radical of first coordinate squared, first coordinate of the vector squared, the second coordinate of the vector squared, plus the third coordinate of vector squared. Here you have 3, 7, and negative 14. 3 squared is 9, 7 squared is 49, and minus 14 squared is 196. If you add them up under the radical, it's going to be 254, and this radical cannot be simplified. So this is the length, exact length of the vector that initiates from the point 2, negative 1, 4, and terminates at the point 5, 6, minus 10. Okay, and similar to the vectors in R2, we can add up or subtract 2 vectors, and also we have scalar multiplication. So addition, subtraction, and scalar multiplication. We are talking about three-dimensional space. So they are in R3. So obviously, if I have two vectors, A1, A2, and A3, also B1, B2, and B3, if I add them up, the outcome A1 plus B1, the first coordinate, A2 plus B2, the second coordinate, and A3 plus B3 will be the third coordinate. In the case of subtraction, suppose instead of plus was minus. So inside the coordinates of these vectors, these pluses will become minus. Also, if I multiply a vector by a real number, a scalar multiplication, so C times A1, A2, A3, that just means that I multiply C by each of these coordinates, CA1, CA2, and CA3. Let's look at an example. Okay, suppose vector U is given as 1, 0, 2, and vector V is given as 2, 1, 1. In part 1, I just want to find 2U minus 3V. To do that, and suppose I want to write my answer in the same notation that the problem was given. If it is given in IJK, I need to respond, or if the problem specifies to use the notation of IJK, I should give the answer in that way. Okay, to do this, again, I'll suggest that you pause the video and try this on your own. So 2 times U means I multiply 2 by all the components of U. 2 times 1 is 2, 2 times 0 is 0, 2 times 2 is 4. So I just multiply 2 by all the components, all the coordinates of U, minus 3V. I multiply 3 by all the components or coordinates of V. 3 times 2, 6, 3 times 1, 3, 3 times 1, 3. So I do the subtraction. 2 minus 6, negative 4. 0 minus 3 is negative 3. 4 minus 3 is 1. So that's again, if the question was to write it in the IJ form, that would have been minus 4I minus 3J plus K. And the second part of this is find the length of what we obtained, the length of 2U minus 3V. Again, please pause the video and try to do this on your own. So here we find the length of, we already found what is 2U minus 3V in part 1. Minus 4 minus 3, 1. If part 1 was not given, we needed first to find 2U minus 3V, as we did, and then find the length. But here, for simplicity, I broke down the example into two parts. Now the length of this is a radical of the sum of these coordinates squared. So radical of -4 squared is 16, -3 squared 9, 1 squared 1, and 16 plus 9 plus 1 is 26. And radical 26 cannot be simplified. So this will be the final answer.